Today's webinar is about the OpenMAPP project, Open Meta-Analysis in Particle Physics. And I'm really pleased that we've got the lead UK participants from OpenMAPP here today to talk about it. I'm just going to give a brief biography for each of them. Andy Buckley is Professor of Particle Physics at the University of Glasgow and is PI on the OpenMAPP project. He is a particle physicist working on the boundaries between experimental studies with the ATLAS experiment, which is part of the Large Hadron Collider, the world's largest and most powerful particle accelerator at CERN in Geneva, and theoretical work on modelling of hadron collisions and on constraining prospective models of new physics. John Butterworth is Professor of Physics and a member of the High Energy Physics Group at University College London. He works on the ATLAS experiment at the CERN Large Hadron Collider and on related particle phenomenology. He has written popular science books, including Smashing Physics, which tells the story of the discovery of the Higgs boson, and for publications including The Guardian newspaper and New Scientist. Christian Gutzjoff, who's not here but may join, is a senior research software developer and particle physicist at University College London. He specialises in sustainable software development and advanced statistical data analysis. His work focuses on creating open source software that delivers high fidelity theoretical simulations designed to model the vast and ever expanding datasets generated by CERN's Large Hadron Collider. And finally, Martin Habedank is a research associate in the Particle Physics Experiment Group at University of Glasgow. His work focuses on the ATLAS experiment at CERN, where he conducts searches for new physics. He specialises in ensuring that the results of these searches remain accessible and usable for long-term future research. So welcome to all our speakers, and I'm going to hand over to Andy to start us off. Thank you.
Thanks very much, Dan. This presentation is to tell you a bit about OpenMAPP and the general issues that we're encountering and trying to do something about when it comes to reproducibility-oriented issues. And in particular, it's reinterpretation. I'll explain later what I mean by reinterpretation for particle physics. So I think that maybe we are the first sort of very physics-oriented project to try and connect and talk to the rest of the UKRN network here. So thank you for having us along, and I hope that this is both accessible and interesting, and that you'll spot various analogues and points of similarity between our domains, even if the raw content is a bit distinct. So what I'll try and talk about, I don't just want to leap into assuming all particle physics, because you're not particle physicists typically. So I will try and rush through particle physics and the idea of what we call new physics at Large Hadron Collider, which will then give me a base to tell you about this idea of reinterpreting analyses, what the obstacles are, what approaches we try and take to enable this and to remove those obstacles, and in particular what the role of this OpenMAPP collaboration is. Okay, so first you get a quick tour of particle physics, and I should say actually John and Martin, who are here as well, if they feel like jumping in at any point, please do. It's down as a joint presentation, and I'm just here to lead the slides, but I think having a bit of a conversation or random inputs would be probably quite fun. Okay, so I don't know how much you remember, or maybe you do this every day, but fundamentally what we're made of, stuff that we might call matter, is quarks and electrons. So up and down quarks and electrons, and these up and down quarks get stuck together inside protons and neutrons, which make nuclei, which make atoms, which make us. So in some ways that would be a neat picture of what reality is made up of, is these things that join together and make nuclei, and electrons buzz around the nuclei, and all other science results from that. One of the weird things that particle physics discovered through the 20th century is that they're not alone. Actually, we get extra copies of these things. We get a sort of heavy version of the up quark, a heavy version of the down quark called charm and strange. We get a heavy version of the electron called the muon, and we get these other weird things that have come in at the same time as the electron and the muon, called neutrinos, which are basically invisible, very, very, very weakly interacting particles, which we weren't aware about for a very long time. The main place that we're influenced by muons in human experience of the world is actually from cosmic rays. There's a lot of high energy particles blasting through space, produced by various astrophysics processes, and when they hit the actually it's often protons coming from the sun that hit the upper atmosphere of the Earth, and they produce a shower of particles. You can see it going on here. And muons are famous for being the particles that shouldn't make it all the way down to Earth, but they do because of some of the effects of Einstein's relativity. Something also quite cool and interesting that muons get used for now is actually using those cosmic ray muons as a way of looking at things like the inside of pyramids to see if you can detect any voids, because sometimes they will hit the rock of the pyramid, and if there isn't any rock there, you get a difference in how the muons make their way through it. And then, even more surprisingly, there was a third of these, what we call generations of particles, adding yet more up and down type quarks, but now really heavy ones called the top and the bottom, and a really heavy version of the electron called the tau and its corresponding neutrino. And these things essentially do not exist anywhere other than at big experimental laboratories where we make them on purpose. So that's the matter. And then the forces. If life is to be interesting at all, the matter needs to be able to interact with itself and with other bits of matter. And to do that, we need to bring in the concept of forces, of which you're probably very familiar with: the electromagnetic force, which acts on electric charge, and gravity, which acts on mass, but maybe less so with the weak and the strong nuclear forces, which the weak force is, among other things, it's responsible for the way that the sun fuses hydrogen nuclei together into helium and produces fusion energy. And the strong forces explains how it is that these quarks can stick together and make protons and neutrons. So at low energies, the strong force binds everything together into these composite particles like the protons and neutrons, but there's a lot more as well. So we get a whole family of these 3-quark things, which are called baryons, and then a big family of quark and anti-quark pairs. I'll come back to anti things later, and none of them are stable. So essentially the only stable quarky things that we know of are the proton and the neutron. But if we go to really high energies, then we start not seeing these things as collective protons and neutrons, but actually as the constituents within, so the quarks that make up the proton. The higher energy that you get, the more we start probing the very small structure. It's a little counterintuitive that you have to build very big detectors and very big accelerators, essentially a several kilometer long microscope here at Stanford Linear Accelerator. To look at the very smallest things, you need very big equipment. And that's essentially because you need something that will get the colliding particle to high enough energy that it's got a wavelength that's very small, and then you can probe tiny structures. So this has been something that's been going on since the sort of early to mid 20th century, and really reached its apotheosis in the 70s, when there was an understanding of these forces and matter in a way that really unified them together, and that involved this concept of the Higgs boson and the Higgs field in the background to these forces and matter particles that gave them mass, and also explained better some of the relations between them. So I can't go into any of that stuff in detail, but it's been quite a journey over a period of roughly 100 years now. I did say I'd come back to antimatter. At least on the quark side, quark and lepton side, we get actually double copies of everything. There's antiparticle, so anti-up, anti-down, anti-strange, anti-charm, etc. And there's an anti-electron called the positron, an anti-muon, and anti-tau. The force particles, so these force things are actually still particles. The nuclear forces, the electromagnetism has the photon as its particle, and so on. They're the antiparticles are in this thing called the W, one of the bosons of one of the particles of the weak force. And the last thing that I'm going to say in my background to the theory of this is about interactions. So we can't just do anything we feel like. You can't just take 2 quark particles and make them. Actually, I should pick something else. I can't take 2 electrons and make them talk to each other through the strong nuclear force, for example. There are rules, and the rules encode what interactions are allowed. And in particular, they're really saying in what ways can I hand energy between these different types of matter particle. And these are encoded in things called Feynman rules, Feynman graphs. And essentially, if you can draw a graph that connects a particular kind of particle to other kinds of particles, that's saying you've got the ability to exchange energy between these things. Although what it looks like is often that one particle has produced another, or that 2 particles have collided and disappeared and produced something new. Okay, that's the theory. What about the experiment? Well, it's quite a simple idea. I've nicked the title of John's book for this slide because essentially it's thuggish physics that we take a particle, we give it loads of kinetic energy, and we thrash it into some other particle as hard as we possibly can. And the cool thing is that these rules and interactions say that we can actually get new stuff out. So you don't just get them bouncing off each other elastically, but actually, if you put enough energy in, you can produce completely new things. That's just by handing energy between these different particle types or fields, as we call them. Martin gave me this lovely cartoon, which I'm just going to give you a moment to look at. It really is quite thuggish stuff that we do. I think we get a reputation, or we think that we have a reputation for being all terribly clever, and with our big machines and stuff. But essentially, what we do is this. It's we hit stuff together, break it apart, and then pick through the remnants and see if we can make any sense of them. So the big famous particle physics lab is the CERN lab in Geneva. This is the center of European particle physics, and I'm sure some non-European particle physicists would complain if I said that it was the center of the world particle physics community, but I think that it is. It's the largest and highest energy particle collider in the world, and if you can see my cursor, can you actually see my cursor here moving around? I'm not sure if you can. Anyone?
We can see it.
Yes.
You can see it. Okay, brilliant. So down here, there's this sort of wedge-shaped collection of buildings. That's actually the CERN main site at Meyrin. In fact, you can see little circles in there, which are old circular accelerators on the scale of the CERN site itself. For reference, this is Geneva Airport over here. That's Lake Geneva. This is the Jura Mountains, and it's wedged into this gap between the Jura and the lake. And you can see coming out of this little accelerator here, you can't quite see the linear part either. Goes into this small ring, which is only a few kilometers long, and then after it's got up to speed in that one, it goes around this massive ring out here, which was built in the 1980s, and I'll tell you in a moment what's in that hole now. So it's a big facility. It's got this site here. It's got another site up at the north side. It's got various points around the countryside between France and Switzerland. And people always ask about what this costs. And I like to point out, well, there's 25 different member states, plus some associate members, like the US is officially not a member because then they'd have to pay a massive joining fee, but they contribute in other ways. The total annual budget, I saw in an update to a Bill Bryson book that's happened. It was described as having a budget the size of the GDP of a small Central American country. It's off by a factor of 10. It's 1.2 billion, which is a lot of money, but I also checked, and it's the same as the added up salaries of Paris Saint-Germain and Manchester City footballers. So I'm not going to risk asking you which one's more important, but you get an awful lot of science out of this facility, whereas you only get a certain amount of football out of the two teams. Okay, so where did this come from? We didn't start by building facilities of that size. It actually started, because I'm in Scotland, I have to say that it started in Scotland with C.T.R. Wilson working at the observatory on top of Ben Nevis, where it was very foggy, and happened to get very interested in atmospheric phenomena. In particular, discovered that you can actually see particle tracks in mist. And if you create a sort of laboratory cloud, you can build a cloud chamber and see subatomic particles passing through. So that led to building bigger and more complicated and more refined machinery, such as this bubble chamber. It's a similar idea, but much better resolution. This is the Gargamel bubble chamber in the gardens at CERN. And eventually we've ended up with equipment like nowadays, which are these giant pieces of equipment full of very high precision, incredibly highly engineered silicon, with fantastic ability to really track individual particles and measure all of their properties as they pass through these gigantic detectors. So about that gigantic detector, this is the Atlas experiment that the three of us here today all work on. We don't usually let people stand on the beam pipe, but they're there for scale. This thing is absolutely whopping. I think it's 20 meters high and 40 meters long is the rough dimensions of this thing. Normally isn't cut apart like this, just so you can see that there's layers and layers and layers of different kinds of detector inside. And typically these things are they are where they are, and they're made of the material that they're made of in order to measure different properties of different types of particle. And then we can, the analogy is smashing some mechanical watches apart, and then looking at all the little cogs and wheels and bits that come out and trying to figure out from those details what's going on. And so we have detectors that are essentially very good at measuring different cogs and bits that come out of our physics watches. And this is what that looks like. If you collide something in the middle, it produces this huge spray of particles that pass through the detector, and we try and figure out what's going on. Okay, so this is my last slide on trying to give you some context. I hope it was useful. What have we learned from this? A load of amazing things, actually, like truly mind-blowing, changes your perception of the universe things. I can start with something almost very difficult to explain, but something we've discovered is that symmetries, mathematically expressed symmetries, seem to be really, really, really important to our universe. There's a sense in which you can say, if you insist on certain symmetries, and by symmetry I mean a thing which, if you take a physical system and you tweak it in some way and nothing changes, nothing observably changes, even though you've redefined bits of your physics, then that's a symmetry of the system. And what we found is that there are certain forms of those symmetries, those operations that we can do that don't change anything, that predict electromagnetism. They predict the nuclear forces. And the big realization in the 60s and 70s was actually these things could even be mixed together in the early universe. And so the form of the symmetry changed at some point in the history of the universe. And the way that breaking of the symmetries between these forces happened actually led to the creation of mass. And the discovery of the Higgs boson at CERN in 2012 was essentially a validation of that. And the work that's been done since then was a validation of that theory about how the symmetries between these different particle and force types and how that changed in the early universe is responsible for the origin of basically everything that we see these days, except perhaps for the neutrinos, which are so weakly interacting and that we still don't quite know exactly what they are. And antimatter also has some, I said that there was an exact copy of everything, and it seems actually in some ways the copy is not exact, and the behaviors between the antimatter and matter are not exact opposites of each other. And finally, something that's really motivated more by cosmology and astrophysics, but we think very likely, as particle physicists, we like to think probably has a particle physics solution, is that 95% of the matter in the universe is not like the matter that we're made of. It's dark matter instead. It's very weakly interacting. It does not luminesce and shine through telescopes. We think perhaps it only interacts through gravity, perhaps it only interacts through the very weak nuclear force. And so that's one of our major motivations, is to try and understand the origins of that stuff that's 95% of the matter in the universe. All right. So, I did have one more slide. I have to say something about the LHC. So my context for all of this is the Large Hadron Collider at CERN. That's the thing that currently sits in that massive 27-kilometer tunnel. It was built in the 80s for electrons, and it ran as something called the Large Electron Positron Collider. The LHC is now the second collider, accelerator that's been put into that tunnel. It's mainly there to collide protons rather than electrons. And there's reasons that using a much heavier particle allows you to get to much higher energies. And then there's actually more experiments. There's actually more experiments in on the ring, but I'm not going to concentrate on those here, I'm afraid. I'll just talk about these ATLAS and CMS, which are what we call general purpose detectors. So in something like ATLAS, you might see events that look like this. If you look down this pipe in a way and try and see what particles are going where in the ATLAS detector, you might see a lot of energy, a lot of particles going in one direction and not so much in the other direction. That would be, for example, a sign of producing dark matter at the LHC. We have some visible standard model stuff that's familiar to us going in one direction, and some invisible dark matter has disappeared in the other direction. Okay, I hope that's a useful bit of context. Do feel free to ask questions about particle physics as well as the preservation if you're interested. Okay, so now I should say something about how do we take events that look like this. All these pictures, you can see lots and lots of little bits drawn on the graphs, drawn on these 3D displays here, and they're sort of meant to represent energy deposits in different kinds of those layers of detector in ATLAS. So if we didn't have a nice picture like this, we just had the numbers coming out, what would we do to that to get some physics out? And actually this data is coming in through millions of these electronic readout channels, and the collisions happen 40 million times a second. So this is very technically challenging to process. And in fact, there's no way that we could write out all of that data into a storage format. And so we first use things called triggers, which are there to throw away the vast majority of events, the collisions, because most of the time we sort of know what's going on in those, or they're not doing the thing that we're interested in. But still, the data flow is pretty massive. So we're writing about 30 petabytes of data every year. So that's 1,000 gigabytes written every year by the LHC experiments. So processing that means that you now need an absolutely massive computing facility. And our computing facility is, well, a lot of computers at CERN itself, but also a worldwide grid of computing farms whose job is to move this data around in the most efficient way that we can, but also to send data selectively or send processing jobs to the places where the relevant data is, and then we can run on it in an efficient way. What we do is we take those millions of signals and through various stages of processing, we turn them into more what we call analysis object data. We construct physics objects, like here's a vector that represents an electron. Here's a number that represents how much invisible energy there was or momentum there was in some event. Rather than, we don't operate on the raw signals all the time. We turn them into more intuitive objects, things that look like particles in a way. That happens to the real data. We actually do a lot of that chain also for simulations, because what we're doing is sufficiently complicated that we can't just analyze the data and compare it to a nice simple function like a straight line fit or something like that. We really need complicated simulations that are based in the theory of particle physics to give us predictions. And we don't absolutely trust the predictions, but they are a very good guide to what we're going to do. And we use those predictions with some understanding of how uncertain they are to actually test a lot of our physics theories, because we can't just draw the line that corresponds to the theory and plot the data on top of it. So a lot of this stuff we do using generative physics models. I say generative because that sounds very very modern in the era of large language models and generative AI. They're more things where we are able to sample from the mathematics of particle physics theory and produce things that look like real collision events. But this is a very expensive thing to do in two stages. One, doing that calculation can be very, very expensive. And then you have to simulate the way that the particles coming out would have interacted with your massive detector, which is also incredibly expensive. So this is not a thing that you want to be doing a lot of. It really requires these kind of worldwide scale computing resources. So this all leads to papers. And so far in the 15 odd years of LHC operation, there's about 3,000 papers out of the LHC experiments. And just as an aside, because we're not here to talk about publication policy and so on, but for your interest, all the publications coming from the CERN experiments are open access. Virtually all of those will be without any article processing charge, because CERN has negotiated a deal with basically the main journals in our field, meaning that we pay one field-wise subscription charge, and then essentially no one has to pay to publish a paper, which I think is a fantastic way for us to operate. It's still evolving. There's still a rise of more kind of completely free or completely self-operated open access. But for your interest, this is a thing that we do in our community. We also publish, we put everything, almost everything, goes on the archive preprint server for free access before it goes anywhere near a journal. Okay, that, you can probably guess from my enthusiasm about this what my opinions are about journals and such like. So there is one problem with these papers, which is great that we produce 3,000 papers, and I think the quality generally is pretty good. They go through these huge collaborations of several thousand people potentially looking at them before they get published, and it's good science. It's robust. It's typically looking at things that are of interest to some people. But with the expense of this data flow, with restrictions of, say, how high dimensional can you make a plot that you put in a journal? Well, pretty much two-dimensional. The experiments are frequently limited to only looking at relatively simple versions of new models. If we had a proposal for some new physics that might happen, that might be very complicated, and instead it gets boiled down into sort of a simple cartoon version of the same thing, because we can think about trying out lots of configurations of the simple cartoon in a way where we really couldn't explore the very complicated, full realistic model. That doesn't mean that it's not interesting to look at realistic models, but it means that we've got to reuse the published data somehow. We're generally speaking, not going to be rerunning over the raw data. So historically, this isn't something that scientific publication policies and so on really incentivized very well. It was more regarded as your job is done as a scientist, as a particle physicist, at the point that you have produced some histograms, some plots, some numbers, and written a paper and got the paper accepted by the journal, then that's your job done. Whereas now, oh, I've got something lying over the text there. Sorry about that. I'll fix that when I upload the slides later. That was not something that we were really encouraged to make it possible and make it easy to take what was published and reuse it and reinterpret it in terms of new models. The thing that's meant to say underneath there, I think, is that the LHC is the first facility to really digitally publish all of our primary data, by which I mean these kind of the plots and the numbers in the plots, and actually all the breakdown of all the uncertainties and all the numbers on the plots in a community facility called HepData. We have this database at hepdata.org, hepdata.net, hepdata.org, I can't remember, which contains data from particle physics from the 1970s onwards, but the LHC was from 2009 was really the first facility to systematically put all of its own data into HepData, rather than HepData kind of scraping through journals and trying to find plots and read data points off the plots. This is something now that we really do by ourselves. We push this data out and put it in a format where it can be reused. So we're getting better at a lot of this stuff. I think the culture has changed. There are a lot of particularly younger scientists who are very motivated by the idea of making this stuff reusable. But I'm going to leave a hanging question, which is this enough? If you just have the data, is the data alone enough to reproduce a result? And by implication, the answer is no, and I'll tell you how the answer is no. So this reinterpretation thing I want to go into a little more detail on. So our jargon here is that the first interpretation, without the re in front of it, that's the thing that gets published in the experimental paper. So the experiment is probably interested in testing some hypothesis, and they'll write a paper which goes through all of the data analysis, what was done to those raw data signals and the physics objects that were constructed and so on, what we did to those, and we'll make a plot and we'll compare that plot to the prediction from, or some predictions from, this hypothesis we were trying to investigate. Often it's in the direction that the analysis was designed to test that hypothesis, rather than just something that happened to come out of it. But then, as I've said, that we don't want that to be limited, that whole study with all that analysis of all that data to be limited to only ever having put restrictions on that one thing that the experiment was interested in. What if people are interested in something else that is similar but not quite the same? So reinterpretation is about making it possible to go back and use that published analysis, published data, but to test new models, test new hypotheses, using that data. But by construction, probably they have to be a bit similar, otherwise the analysis won't have any relevance. But we want to be able to use these things for general purpose, and we want to be able to keep that scientific impact going for in perpetuity, as long as we can, essentially. You know, we have data sets from 1990 that we still use. That's now approaching 40 years ago. It's fantastic that that's possible. We want that to be the norm. In fact, we want people to be using LHC data sets 50 to 100 years from now. So this idea of reinterpretation has really been growing and becoming quite a major activity through the 15 odd years of LHC operation. And one of the things I think is really good about it is that it naturally sits across the boundaries of theory and experiment, and it helps to break down the borders between us, which are sometimes a bit artificial, that people feel they can only talk to their own tribe. And I think it is the key to getting the most science out of this big public facility investment, which, as I've said, is almost as big as 2 football teams worth of fancy players. And you can also phrase this as a sustainability thing. We're trying to get, by some metric, the maximum amount of physics per ton of carbon dioxide that we produce in these colliders. They are not necessarily environmentally friendly things. Therefore, there's a natural sort of moral requirement on us that we do everything that we can to get the most science out of these facilities. All right. So one thing that we've done along the way, this grassroots activity, has been the LHC Reinterpretation Forum, which really popped up out of nowhere and has for 10 plus years been a source of driving recommendations and getting people together to talk to each other about challenges and requirements and what data we need and what is needed to be able to reuse published data from the experiments. And when an analysis is done in a way that isn't good for reinterpretation or that has accidentally shot itself in the foot, this forum was there to discuss that and to come up with recommendations and talk to the relevant people and try and prod everything in the right direction. So there was this paper that came out in 2020, following up on another one that had been several years before. And these are really useful internally for us to write some briefing notes that are relatively frank about where we're doing well, where we're not doing well, and to give really concrete advice on how to do better. And it's been sufficiently successful. I mean, this is going to sound enormously bureaucratic, but it's now an official sort of operation of the LHC Physics Centre at CERN, Beyond Standard Model Physics Working Group. Now, this sounds awful. It's a good thing. This means that something that was originally just a grassroots, a few physicists talking to each other and grumbling, has turned into something that's really recognized officially by the community as an activity that we should be doing and that deserves some officialdom and implicitly there's a bit of finance behind this and the ability to make some things happen. So it's nice to see that this grassroots thing is actually being officially recognized and taking off. It's things like this have also made their way into, for example, we're doing a big Europe-wide re-evaluation of strategy in particle physics and what future facilities we'd like to operate and what physics we think is most important. And it's nice that we see this stuff, the sustainability and the reproducibility is appearing there now in a way that, if you go back 10, 15 years pre-LHC, I don't think that would have been there at all. So for connecting to the rest of your disciplines, I think what I've heard about is the reproducibility crisis in various subjects of studies which have been influential in the field, and everyone has operated on the assumption that they are true and proven, and then attempts to repeat the experiments or to repeat the exercise have not been able to reproduce the results. And of course, this means that whole chunks of the field might have been for a long time based on foundations of sand. And I don't think we're in quite that situation for particle physics. I think maybe the nature of being such big collaborative science, I mean, I didn't say how big the experiments are, but Atlas and CMS each have about 3,000 researchers and staff working on them. There is something about the collaborative nature of it and the ability to work together in quite an organized and quasi-industrial way, like this ability to do a deal with publishers. That means that sometimes we're quite good at collective action. We've always been quite obsessed with say, numerical precision and faithfulness and understanding our uncertainties in a way that's very, very detailed and reporting that stuff in a way that's detailed. We've been getting better at it as well, but we shouldn't pat ourselves on the back too much. There are definitely places where particle physics, for example, is preserving the data very well, but maybe we haven't preserved other aspects that are just as important for actually doing reproduction. Okay, so this reproducibility then, the most obvious way to do reproducibility is to publish the raw data. And I've got a link here on the right to the CERN Open Data Portal, which is the sort of coordinating effort at CERN for doing this publication of all our raw data. There are about 100 petabytes written to tape and disk at CERN. That is a ridiculous amount of data. And realistically, unless you are one of the LHC experiments or a mega tech company or a terrifying government organization, there's no way that you're going to have the computing power to run over 100 petabytes. I mean, physicists at the LHC do not run over 100 petabytes. That stuff is coordinated by the experiments, and it gets fed down through this chain of making simpler and simpler data formats until you've got something that's on the scale of, say, many terabytes rather than petabytes to deal with. arguably the bigger issue anyway, not just the size of the data, is the software quality. And by that, I largely mean the documentation, and that a lot of this software is not written for general use. It's not an app. It's written for use in the context of the experiment, for operation by experts in the experiment who spent a long time learning how to run each bit of it. It's not something where we just dump out several gigabytes of software and say to an external user, use this. It's not going to happen, even if they have the computing power. This has been a big challenge. It's maybe the reason that we're a little late to the open data game. There are some other bits of physics, like gravitational waves, for example, that are ahead of us in this. But our software processing is very, very, very complicated. But the politics, it's nice to see, has been solved, or in principle, and we've agreed now, and that there's a commitment that we release 25% of the data of sort of raw data from a collider run, physics useful data from a collider run, within 5 years of the run finishing, which is good. And I think actually realistically we're doing a lot more than that now. There's much more of an intention to release the full data set on a longer time scale. The 5 years is sort of necessary because actually the internal analyses can take up to that long to process the data and to understand everything in detail. And we do think that the experiment should have the right to analyze its own data first. But this is a good move, and the plans to release data and also to release predictions are really improving and getting much, much better. The data that's released here is not the full stuff. It's the more reduced data types. And it's not entirely clear how much of this is in the balance of this is nice stuff to use for outreach to schools versus how much is actually for novel science. Right, I'm going to talk then about a more lightweight approach to this and try and finish myself up relatively soon, actually, so that we have time to have a bit of Q&A. So Monte Carlo I talked a little bit about earlier. That's the simulation chain. And we have a sort of market of tools that's popped up to do reinterpretations of Monte Carlo models, MC models of new physics processes. So the main sources of data to compare to is this HepData community database that's operated out of Durham, and Graham Watt from the Durham Institute of Particle Physics Phenomenology is also on our OpenMAPP team. And then we have various bits of software which exist to do reanalysis on cheap simulations. So rather than this big, heavy, massive CERN chain of stuff, we do it on relatively quick simulations instead. There's also a whole load of tools have popped up to do the statistics, because we do very, very detailed sort of statistical combination of this. There are also ways of doing a full detail analysis preservation where we're storing everything that the experiment did on the really full-size data sets. I'm not going to talk about that. I think it's important that we do it, just as for storage of what it is that we did. It's high fidelity recording of what it was that we originally did. But in practice, a lot of the time this turns out to be just too expensive to use. And because the sort of saved version of the exact analysis code is from the era in which that analysis was done, this has to be packaged up in a way that's not very flexible to use afterwards. So what I'm going to talk about in the next few slides is focusing on two of these tools, which are Rivet and Contour, which are a lightweight tool and a lightweight interpretation on top of that. So Rivet's job, I'm going to say very quickly, is to take in these collision events, some record of the collision events, and to measure what we call observables. Anything that we could have counted, say, count how many particles went in a certain direction, count how much energy went in a certain direction, add up all the momentum vectors and say what the total is. It's not really rocket science, but it's good to have a well-engineered tool for doing this in an efficient way. So the development of that is very UK-centric from Glasgow and UCL. And to give us an idea of how influential it is, we have about 2,000 analyses, not all from the LHC, encoded, and you can see over time we've had this sort of increasing function of how rapidly we get new analyses into the framework. For the inside detail of what it does, well, these Monte Carlo simulations create very, very large graphs of particle interactions or simulations of what we think the particles were doing. And Rivet's job is to take this graph, tear it apart, and work out stuff that's actually physical rather than just a record of what happened inside this bit of software. and produce some nice histogram like this at the end, which we can compare. We can compare the data with some predictions. And broadly speaking, this works. So reinterpreting searches for new physics using this kind of quick system actually works really quite well. You can see all these lines here are showing different reinterpretation frameworks and their attempts to model the same thing. And you can see they're broadly in agreement to within sort of 10 or 20%, which for a lot of this beyond standard model physics is actually good enough. It's good enough to point us in the direction of what the experiment should go back and now look at in more detail, which is a good mode to be in. We're not trying to create a system by which experiments can be replaced. The experiments fundamentally are the experts in their own data, but this gives a route for a better interoperation with the theory community as well. I'll just say at the bottom that we do a lot of machine learning and AI-based methods these days, and there's nothing wrong with using those as well in these kinds of frameworks. So we're not just limited to what can be done with these direct searches, so something where you go out and explicitly look for some new model of physics beyond the standard model. But the LHC does a lot of measurements which don't assume any particular model, or they shouldn't assume any particular model. They just choose events which meet some criteria, and they measure some properties of those events, and they try and correct those measurements for biases that came in because our detector was not perfect. Sometimes it gets the numbers a bit wrong. Sometimes it skews things in a particular way, and we try and offset that. So these things were not done with the job of finding new physics. They're there really to test the standard model. But that means that if you have something beyond the standard model that would stick up like a sore thumb, if we compare it on the right observable, we can use these model-independent tests as a way of constraining all sorts of new new hypotheses that get proposed. So this contour toolkit, for example, it injects on top of a standard model background, the stuff that we believe is there. It'll inject what if there was this much new physics as well, and it looked like this. So if you look then at observables, things that you can calculate from the events, here's a plot, for example, of what we call leading jet PT. I don't need to say what that is, but you can see here there's some red line following some black dots with error bars, and there's just by eye, there's pretty good agreement of this. And that shows down here that how many sigmas of deviation are there between the data and the background simulation, and not very much, very small deviations. But if you inject the right kind of new hypothesis model, maybe that creates something like an actually large deviation here in this last bin. In particular, you see this, suddenly it pops up, it doesn't fit the data very well anymore. And that would be, if we see a lot of those sorts of deviations, that actually allows us to say maybe the standard model is not true. Doing it this way with these fast simulations, with this just injecting new things on top of the prediction, that means that we can also be very fast. And the great thing about being very fast is that rather than being restricted to these cartoon models, you can really look at a huge number of variations of much more complicated models. This is something that came out of a study we did quite a few years ago now. But when we sent it to the journal, they said, that's interesting, but could you do it for a few more variations, maybe 7 of these multiplet things and 3 generation couplings each time and 4 other couplings and 300 points per. If you multiply all of these numbers together, you get essentially the number of events that we needed to simulate and pass through this framework. And actually, it only took a month to do all of these. So every one of these squares here is one of these 300-point scans telling us something about the physics for yet another proposed model of new physics. And I think there's about 3 times more plots than this at the end. So if we do this well, we can measure things in lots of different ways, and then can go back afterwards and test really complicated, really general, really interesting physics models, ideally forever. And I think I will just skip over this one actually, which is to say that you can also think about then combining them together, not just using one analysis at a time, but I could actually maybe use multiple analyses at the same time, if I'm careful about the ways in which those analyses are related to each other and the ways that they would correlate together. All right, so I'm really coming to the end, I promise. I haven't mentioned OpenMAPP yet. I've mentioned all of these different frameworks and activities, ways to try and coordinate and improve what we do. OpenMAPP is an organization that works within this this picture of lots of originally grassroots and increasingly a bit more top-down organized activities to allow better reproduction, better reinterpretation. It's because we can't just operate on the basis of people gifting their time without having any institutional support. And having the infrastructure to do it, having technical tools, having someone to coordinate something, having some technical standards so that everyone is working in the same way really helps. So OpenMAPP is a project funded by CHIST ERA. Don't ask me what it stands for, I haven't yet found out, but they very nicely funded this as a joint project across UK, France, Poland and Turkey. And I think the Turkey note includes Korea in one of those strange twists of funding fate. So this, from our point of view, within the UK, Contour and HEP data within this are really leading, extending HEP data to store better the experiment's theory estimates. So we're not just getting the data stored in the real data stored, but we're also getting the predictions, because often these background predictions are so expensive that that's another thing that people couldn't make by themselves. We really need to, the CERN, the experiments themselves that had all of that CPU power to provide, to store and publish that data so it can be reused. And to make this queryable. So we're trying to make the data discoverable on HEP data. At the moment, you can discover by manually walking your way around the website with your trackpad and mouse pointer. We want to do something where we can much more have a computer readable way that we can exchange data and we can cross-reference and we can start digging into the details and figuring out, for example, what are interesting kinds of observables that haven't been measured yet, or where there are limitations on what sort of models we can test. Can we identify what those are and better target what we do in future? One of the ways that we want to link this stuff up to join together the analysis logic that comes in from Rivet and other analysis tools, and the data from HEP data and the publications that sit in our publication database called Inspire, is by using DOI identifiers and also exchanging data formats between these different tools so that they have an awareness of each other's content and where there are overlaps, and so that we can get a much better picture of, in a unified way, everything that is available. And that makes it possible for us then to get a global picture of what questions we could ask about new models. And I've put here an infinitely open-ended last bullet to say we're doing technical work on unifying interfaces for these tools and unifying the kind of output formats and how we do the statistics and how we combine things, how we use AI algorithms in these reinterpretations and so on. Okay, so I'm at the end now. I'll just summarize to say the LHC has published well over 2,000 papers, almost 3,000 papers since we started in 2009. That did include, I used to say Nobel Prize winning, actually it's multiple prizes have now come away for the Higgs boson discovery and for other general 15 years of probing the standard model and probing the nature of reality. We don't have any sign of simple new physics theories. That's in a way a positive result of that time, is that we've ruled out an enormous number of simple theories. It does mean that we now need to focus ourselves on more complicated theories and not just trying to get papers out, but really trying to do as good science as we can and making sure that every paper has the knock-on effect of enabling as many other papers, as much other science as possible. And to do this, it's really important that we record not just our data, but also our predictions, our simulation, and our analysis logic as well in a way that can be rerun, because that's how we get the most out of the public investment in this. It's how that we get the most out of the CO2 investment in these facilities. And OpenMAPP is part, I would say actually probably one of the major parts, one of the most active parts of the community in actually developing and trying to push forwards this activity. So thank you very much. I'm very open to questions. We all are. So thank you.
Thank you so much, Andy. That was just fantastic. Thank you. Yeah, please feel free to put your hand up and ask a question. But also I can see there's one in the chat from Neil Jacobs who asks, are there other scientific fields outside new physics that could share many of the challenges and approaches that you've outlined?
I think that's actually my interest, or our interest in joining and engaging with the UK Reproducibility Network is that we don't really know. Everyone is within their own field. I think that we have advantages in various ways because our data is very numeric, and we have such a large history of dealing with large volumes of computing-oriented computer process data. So maybe you'd be looking at other fields. I know, for example, if you look at the very neighboring fields of nuclear physics and atomic physics, then yes, I think very, very similar issues. I think the collectivity of particle physics, the fact that we have these big collaborations, it has allowed us to do things like setting up these databases that have run since the 70s. That's something that has enabled us to get a little bit ahead, I think. I hope that there are some things that we do that can be learned from. I also hope that some other people are doing things that we can learn from.
Thank you. Does anyone else have questions?
So maybe I could just add a comment to Andy's answer there. So I think definitely one of the reasons that we're here is to try and find out that. But I know that, for instance, the Monte Carlo approach that Andy talked about in terms of simulation is quite powerful and not as widely used as I thought it was. So the idea is here that you build something up from the bottom, you understand some underlying principles, and you try and see how they play out using pseudo-random number generators. This is not far away from what's going on, for instance, in climate modeling and epidemiology, and also cosmology, which is much closer to what we do. I think there's a lot less use of that approach than I thought there was. A lot of those models tend to be top-down, and it's essentially very descriptive, whereas I think there's a lot to be said for encoding what you do know in terms of, say, interaction between groups of people, and then seeing how that plays out. But you have to then see the emergent phenomena from that and compare that to the data at the end that you have. And I think, and that's quite computationally expensive and has a lot of the same challenges that we have, in that we think we understand the basic physical laws, but we don't understand necessarily what they lead to in a proton-proton collision. I think that model, that relating a few known basic principles, but a rather complex system that they're operating within, does have quite a lot of application and commonality. And then a lot of the challenges about storing the predictions and evaluate and making best use of the processing time and of the data sets you have are probably very similar.
Yeah, I think technology like that, and I've brushed over the AI machine learning stuff a bit, but these technologies like Monte Carlo, like AI, are very useful. They're very useful for doing powerful things, especially where you can't just write down the equation of what something should look like. But by their nature, that means that it's more complicated to store them in a way that's genuinely stable and can be reused. And certainly with AI type models, we're still very early on in trying to figure out how do we store these things in a way that will always behave the same forever? Because that's not typically the interest of industry. They want to write a model that they can train in one place and use in another one, but next year they have no interest in that. They want to throw it away. We really need to be curating and looking after not just the data, but those algorithms and those machine learning models in a way which we can run forever. And definitely we don't have all the answers, and I'm sure that there are an absolute ton of other fields that are going to have exactly that question as well.
Thank you. I'm going back to Neil's reply to that, which is there a place to explore these similarities? So do places like, I assume he means the National Physics Laboratory, have a role here?
I
might try and defer to John on that one.
He's got a thought. Answer to that question. I mean, I hope this UK Reproducibility Network might provide that kind of forums, actually. Certainly with the NPL, we do work with the NPL. That is a National Physical Laboratory, yes. We work with them quite closely, but it tends to be actually more on hardware and instrumentation development rather than on the software and data analysis at the moment. That's certainly from the UCL and particle physics point of view. We're working on quantum technology with NPL, but we're not actually at the moment working on any software development with them. If there are areas there if there are groups there that we should be talking to, then please get in touch with me afterwards, or Andy, and I'm sure we can do that. But I also hope that, I mean, my understanding is this forum, this network itself, is supposed to provide some of that a forum where we can have those kind of discussions. So maybe we can follow that up here with Diane.
Yes, absolutely. Thank you. Going back to the chat, Holly Ranger from University of Sheffield says, fascinating, thank you, much to think about. I think there are many medical subdisciplines who could relate to your challenges. They also generate huge amounts of data, and your emphasis on reinterpretation would resonate, I think.
Well, that's great. We'd love to we'd love to have the conversation. That's exactly what we're here for.
Another comment is from Judith Winters, who's University of York. I'm not sure we're at the same scale in archaeology, but the new Heritage Science Data Service may also be thinking about some of these issues, and she's given a link there as well. Yeah,
I mean, archaeology, it seems like the sort of canonical discipline in which being able to curate things accurately for a long time is important, and I guess has gone more digital. Yeah, again, very interesting. If I can say one thing actually on the mention of the National Physical Laboratory and so on, is that there are other labs as well, which maybe historically were quite particle physicsy labs and are not so much anymore. And I'm particularly thinking of the Rutherford Appleton lab, which is home to the Diamond Light Source, and I don't know if ISIS neutron source is still there. So there's a lot of material science, and I think more sort of bioscience adjacent stuff going on there as well. And there's a big particle physics connection at RAL. That might be a place that could serve some role in connecting those communities as well.
I'm afraid I'm also going to have to leave now. I know we're losing people quite quickly. I also have another meeting I have to run to. Sorry, but thanks a lot, Andy, for speaking up for us, and thanks for making this connection, Dan.
Thank you. Thanks very much. Thank you, John. Yeah, I think, yeah, people are leaving, so I think we'll wrap up now. But yeah, we'll definitely be in touch and see how we can move forward with this. So thank you so much for today to all our speakers and for everyone joining us. So thank you. Hello, Martin, and thank you.
Bye-bye.
Thanks.